I think we can start. Welcome back, everyone. Well, we had a really weird situation happen with the snow day, so we're going to make some adjustments for our upcoming exam too. But before we talk about all that, were there any questions or comments folks would like to start us out with today? Okay. Well, what happened was we were expected to have a review day on Monday, but the university wisely canceled all operations, so we're moving our review date to today. That means we possibly could have moved our exam two to next week on Monday. The reason I decided that was not a good idea was the turnaround time is huge from the Pocatello Testing Center. And I wouldn't want to give folks their exams back way after spring break ended. That's a really long turnaround. So instead of doing an ordinary exam, we're going to do it as a take-home exam. Today was going to be a review. And when we come back on next Monday's class, the second exam is already going to be open as a take-home exam. I'm probably going to open it on Monday right around noon or thereabout. So think of it as kind of a shorter homework assignment with a faster turnaround date. It'll be due at 5:30 p.m. on Wednesday of that class. And that'll be our last thing we're going to tie off before going to spring break. I should have those graded as well, probably on Friday of that week, so that you'll have your grades back and that kind of stuff going into the spring break. So that's our plan of attack so far. Any questions or comments about that so far, folks? Because I probably have a question. Usually when people say an exam is going to turn into a take-home exam, me personally, I get a lot of anxiety out of that because sometimes that means it's going to be a really long, very difficult kind of exam. But that's not what I'm going to do with this. I've already actually written exam two. It's going to be in the same kind of format. So it's not going to be overly long, overly complicated just because it's a take-home exam. It also means some of these things are kind of weird here. Like, for example, the formula sheet is of less value if it's going to be a take-home exam. As a take-home exam, it's understood it's now open notes, open book, and open calculator. So think of it again as kind of a glorified homework assignment. I'll still put this on the end page of the exam just because, I mean, we said we would, and it might be useful. It's a nice one-stop shop to find all the formulas and things you'll need. And these are still pretty good review problems. I'm still going to write it as if it was an ordinary exam too. So it's mainly going to be about concepts more than anything. So that's going to be our plan so far. So today we'll review for the exam. We'll take as many questions as folks have. If we run out of questions, we'll go to chapter 17, but any work we do in chapter 17 is review for exam two, because we'll be focusing on interpretations and that kind of stuff as well. And I think at that point, I kind of ran out of stuff to discuss. Any questions so far, folks? Okay, so that's going to be our plan for upcoming exam two. And I guess this is the point where we'll turn the class over to you folks. This will be our second student-directed review. We'll do this again for the third exam. This will be a normal exam. We won't be kind of in a corner with spring break and other issues. So we'll have an in-class ordinary exam for that one. But at this point, let's turn it over to the class. What kind of folks or questions or problems would you all like to take a look at for a review? Kind of hard to get started, but no worries. If anyone has a problem, yeah. So gotcha. So number 4, this one right here. I think it's a pretty good one to take a look at. Let me see if I can pull that up. And Abby asks, how do we know to use the lower tail function? That's a good question as well. So let's take a look at this one here as a question. And then we'll take a look at number 4 here as well. I think I have a better way to open that one up. Let's do it this way so we can modify it a little bit better. And everything we do today on the review, it's going into a new document called Exam 2 Class Review. And I'll upload it to this spot, probably on the very top right here after the work is done, if you want to come back to that document. So let's take a look at these problems so far. And let's go with Abby's question first, then we'll take a look at the one above. Abby asks, how do we know to use the lower tail function? There's a lot of kind of context where that could come up. So say, for example, you have a null hypothesis. Let's just put something generic, mu equals 7, no idea what the context would be. And we're testing this against an alternative hypothesis. HA mu greater than 7. So right here, this is going to be a scenario where we would use lower dot tail as false. The way it would come up is we'd have to calculate the Z test statistic. There'll be X bar minus 7 coming from the null hypothesis, divided by sigma over the square root of n. After we have that Z value, the P value for the test is going to be P norm Z, but only because of this right here, it being a right tail test, we insert lower dot tail equals false to finish the p-value computation down there. So if you have a right direction here for a right tail test, that's when that would come up. Other questions about that so far? Okay, well, let's take a look at the example for here. This one's tough because it's a purely just a concept kind of question. It says, suppose we have computed a 95 level confidence interval. We have an interval then from A to B, and the interval was for mu. So in other words, we have found that A is less than mu is less than B at that 95% confidence level. Now, these are pretty tricky. It says true or false. If we randomly select an individual from the population, there's a 95% chance the individual is in AB. How do folks feel about this one? True or false? I agree. This one is definitely false. And the way we can see it is pretty much from right here. The thing that's captured in the interval from A to B wasn't an individual. It's the average of every single individual in the whole population. I agree with Zachary. So here we can just say that this one is false. And did it ask for an explanation? That's always something good to look for. If an exam question doesn't ask you to explain yourself, then you can just move along ahead. That's more for timing if it was an in-class time exam. As a take-home exam, it's completely your option. If it did say explain here, we're required to. Let's put an explanation just for the sake of, I mean, it is a review day. So let's review by saying false, since it is the average, or you could say mean here, of the entire population. That is between A and B. And I always get kind of uncomfortable when I say this, the average of the entire population that is between A and B, because we don't necessarily know that. It might be in the interval, it might be far away from the interval. We just have a level of confidence that the method actually works. So I'd probably put here with 95% confidence, just to make that statement totally correct. We have no idea if the parameter mu is really in the interval or not. Well, that's how that one goes down. And for just as tricky of a question, true or false, there's a 95% chance that X bar is in AB. This one's silly in a way. There's a couple ways that's kind of false. I think we have an open mic. Let me fix that real quick. But any volunteers for why this one would definitely be false? Or excuse me. Well, yeah, it's definitely false. In a certain sense, there's a level of truthness to it. It's kind of confusing. Anyone see what's going on with this one here? Why false is probably the better answer to give. I would say probably the best way to resolve this one is when you take a look at the actual interval A, B, we have to think about how do we even generate the lower bound A, the upper bound B. They came through from this formula. X bar plus or minus Z star, I don't like that minus, let me fix that there, times sigma over the square root of n. Because this is the method that actually calculated the whole confidence interval, what it implies is X bar itself has 100% chance of being in there. It's in fact the dead center. So that's what makes this one false, but also a pretty confusing question all at once. So we can say false since X bar is in the center of that interval AB. So this should say 100%, or as in there is a 100% chance your sample mean is inside the interval. It is our best guess of the unknown parameter mu, so it should be directly in the middle of that interval as well, if that method is working as intended. Oh, then from here on out, these ones are not too bad. It says if the sample size were to increase, would the confidence interval become wider or narrower? Any volunteers say over Zoom, was this one wider or narrower? Jackson says narrower, and I absolutely agree. Thanks, Jackson. What makes this one narrower is from right here. They said the sample size was going to increase, but if you increase the sample size, this entire quantity just gets smaller and smaller. That's the thing we refer to as M, the margin of error in chapters 15. Sorry, those chapters are running together a little bit. So increase the sample size, your margin of error gets smaller. That's just going to make the width of your whole interval smaller at the same time. And I guess the fastest way to say this is narrower, since the larger n gets, the smaller, or hence narrower will get, the smaller m, which is z star, times sigma over the square root of n, becomes. Only because that n is down here in the denominator. So that's a scenario on this one. And same kind of idea in part D. It says, if the confidence level were to decrease to 90%, actually, I think this one's kind of a nasty one. To me, this is a trickier concept question. We're dropping down the level of confidence to a lower level, 90%. We wonder, would the resulting, I think that's not quite grammatical, let's see if we can fix it. Would the resulting confidence interval become wider or narrower? Anyone see what should happen in this direction? It turns out this one goes narrower, but that's what makes this one kind of weirder in a way. To me, the big problem with this is it feels like if you do something that's not great, you're dropping confidence, we should be punished and make the interval wider, but it actually goes the other way, and it's unfortunate. It makes it narrower, and the reason for this is at a lower confidence, the value of z star gets smaller. But if z star gets smaller, it's right here in the margin of error. The whole margin of error itself gets smaller. And again, that's always really kind of weird. Sometimes seeing is believing. So let's actually calculate this and add it. Well, we don't have to add it, but let's just visualize this. If we had, say, confidence set to 95%, we know what z star ought to be. It's about 1.960. Let's calculate it exactly. It would be negative qt, well, that's the new method, q norm for the normal distribution. Take 1 minus c, divide by 2. And there's our 1.96. So that's the quantity that would go right here for the place of z star. But now if we decrease confidence to 90%, there it is, right at 90%. Now this thing drops down to a 1.64, so it's a pretty substantial reduction. But smaller value here now means the whole interval became narrower because of that. Again, this is unfortunate in a certain sense. It feels like if we are less confident, we should be punished, not rewarded, but that's what happens with statistics. And this is the fundamental reason why we always report the level of confidence, even with statements right here, just to be specific what really happened. But any questions, folks, with that one there? Okay, so part D is a huge reversal of expectations on those directions. Then finally, part E asks, When we give a practical conclusion, we state the confidence level. However, we do not consider the confidence level as being the probability mu is inside A and B. What does the confidence level represent? Well, the best way to say this is we can say the confidence level represents the success rate for that entire method. Let's say the entire method of producing AB, that original confidence interval in the problem. So what I mean by success is either mu is inside that interval or it's not inside. There's no probability about it. But every time you go to calculate a confidence interval, the method itself has a success rate of truly capturing the parameter or failing to do so. So said another way, let's type this one out. If we collect 100 different simple random samples, we have to have the exact same sample size to make each one of these experiments equivalent. So let's say all with the same sample size, then a bunch of things are going to happen. You'll have 100 different sample means X bar. We will produce 100 different sample means, which then results in 100 different confidence intervals. That is a really long run-on sentence. Let's start a new one. But now that we have 100 different confidence intervals, about 95 of the 100 intervals will truly contain the unknown parameter mu. And that's what we mean by having a 95% confidence interval. Let's say here, just to tie this off, provided the confidence level is 95%. That's a pretty long-winded statement, but if we ever have to be really, really specific or defend what we mean by success rate here, that's what we really mean altogether. I'd say this is a fine way to answer the question because we're conveying what we're really meaning. But if you want to say what the definition of success rate is, it's all inside there. Well, any questions at all, folks, on getting through that portion? Okay, these kinds of concept questions are definitely kind of tough, but they get a little bit sketchy whenever you're looking at a new method, whether it's a confidence interval, a hypothesis test, or type 1, type 2 errors in power for the first time. But after that, all the surprises are gone. And when we go to chapters 17, 18, and 19, it'll just feel like the same kind of things are applying. It's different confidence intervals, but all of the concepts are the same, and same for hypothesis testing. Well, I think we've gotten through this question. Any other questions folks would like to take a look at very next? Yeah, absolutely. Which one did you have in mind? Gotcha. Let's take a look. And let me see here. Where would I pull that? Should go to the Moodle website. Okay, here we go. I think this one's a pretty tough one. So I think this is a good idea for the purpose of studying for the upcoming exam. So it says here to start, distributions of heights of young American, let me make sure. Am I in the right section? Homework 6, gotcha. No worries, that was my fault. I should have known we were meaning that one down below. So let's take a look. There we go. This one looks harder, so I think we're on the right track for this one for sure. So this one, oh yeah. For me, this one was a really tough problem because it's hard to wrap your head around what they're even saying right here. It takes a few reading throughs to get a feel for it. So let me carry it up to here. And in this question, was there a specific part you want to take a look at in particular? Mostly on part E to take a look at. Gotcha. So let's start off with just the overall problem right here and see if we can get a feel for what's going on. It says a quality control engineer plans to plans to assess the impact of storage on the sweetness of a new cola. So we don't want the Coca-Cola to lose sweetness. Abby asks, can we do everything? You know, why not? This is your review, so I think we can. That wouldn't be a bad idea. Thanks for asking, Abby. It never hurts to ask. So let's start running through this and see what's going on here. Quality control engineer plans a study to assess the impact of storage on the sweetness of a new cola. 15 trained testers are available to rate the cola's sweetness on a 10-point scale before and after storage. So now it sounds like a sample size of 10 people are involved in this. Just in case that's pertinent, let me write down n equals 15, just so I don't forget. So each tester's judgment on loss of sweetness can be assessed. So we have 15 people, they all have their own judgment of sweetness, but they've been trained, so we're going to trust them on it. Next, it goes on to say, industry records indicate that sweetness loss scores vary from taster to taster according to a normal distribution with a standard deviation of about sigma equals 1. That's kind of nice. They just said, use that value, sigma equals 1. I'll just put it here just so it's more available. To see if the taste test gives a reason to think that the cola does lose sweetness, here's where I get hung up. What does it mean to lose sweetness? Let's take a look again. Industry records that sweetness loss scores vary from taster to taster according to a normal distribution with standard deviation of about 1. So we're talking about losing sweetness. A score of 0 sounds like no sweetness was lost at all. Your colas were just fine after sitting in storage for however long. This is saying we have lost sweetness if the value of mu is greater than 0. So this is now saying for all trained testers, that would be the population, they would say that there's a positive score right here, meaning it lost sweetness. So a score is greater than 1 is losing sweetness in this context. That's pretty confusing to me. How do folks feel about that? Does that make sense? Okay, awesome. It's just kind of a weird scale. So a point going up, again, it's a reverse directionality. That's always kind of hard on the mind. So point higher means more loss in sweetness. Kind of a weird scale they decide to use. So now they go on to say, using a significance at 0.05, that right there is saying the significance level alpha is 0.05, and mu is the true average loss of sweetness. That wasn't wonderfully descriptive, but I would imagine they're talking about that true average loss of sweetness for all trained testers, because the sample size only involves trained testers in this industry. I agree with Abby on this one. This one is pretty rough in a way. But after getting through all of that, let's see what's coming up next. I think I have just about everything we can deal with here. We know it's a right tail test. And the next portion says, give a practical interpretation of a type 1, type 2 error represents using the context of the study. Now, there's a great way to start this kind of problem. First thing you might want to say is, in a type 1 error, I'm not going to write down the practical interpretation yet. I just want to organize my thoughts. We want to say what happens in a type 1 error. We made a conclusion that was false. I mean, it was an error. So what happened? We reject a null hypothesis. We concluded this is true, when in fact, that was true. The null saying there no sweetness loss actually occurred. So that's how I'd probably organize my thoughts. We concluded HA is true. when H naught is actually true. Now, that's the organizing statements. We have to actually write it out. This is the hardest part. Any questions so far, folks, to this stage of the organization? Okay, so it says, give a practical interpretation. That means we're going to write out a statement that doesn't use any special symbols, terminology, or that kind of thing for what type 1 represents. And we have to pull in the context as well. So we need to be talking about loss of sweetness in the cola. First, this is what we would have concluded. Let's just write this out, that the study concluded that mu greater than 0 would mean the average loss of sweetness for the cola, some new cola, they said, let's go with new cola, is greater than 0. That's a problem because now it means the stock is compromised. If we made that conclusion, they might destroy it or something along those kinds of lines, or maybe just discount it, who knows. But this was a statement in error. It was, in fact, this was what was true. There was no actual loss of sweetness, meaning we've overreacted, we possibly destroyed product when we shouldn't have. This could be a huge financial loss for the company. So we say down below, when in fact, there was no loss of sweetness. So we did it, folks. That's what happens in a type 1 error. Any questions at the moment? Okay, now we're going to go for a type 2 error. And type 2 error, in my opinion, is definitely kind of tricky. What makes this tricky is you can describe a type 2 error just fine, but if you want to calculate power, or if you want to calculate the probability of a type 2 error, there is not enough information in this problem to do it whatsoever. You need to have a notion of effect size that the experts are really worried about, and you need to have a specific alternative hypothesis that you're testing. So writing out a type 2 error here feels a little bit funny, but it can be done. Here's how it's going to go down. Let's do the same kind of thing that we did here. We want to organize how we're going to write it out before we dive in head first. So let's say what happens in type 2. So the type 2 error, let's write out, we failed to show something. We failed to conclude HA is true when in fact it really is. Now this could be possibly even more damaging for the company. If this is true, that means the cola that was in storage really lost sweetness and it's going to taste very bad when they release it to the market. But if they fail to detect that and they release this new cola to the market, that new cola is just doomed. Think of things like, what were some new colas back in the day, like Crystal Clear Cola, things like that. They don't do the testing just right on this thing, then the product is going to be doomed. So type 2 error might be the more serious thing for the company. You never want to release a product that's just not up to par. But let's actually write this out. That's the challenge on this. Again, the trouble is you want to focus on what the study is actually going to do in a type 1 error. In a type 1 error, you concluded that's true and it's false. Same for a type 2 error, focus on the conclusion that would actually be given. So in a type 2 error, we go over here and say the study failed to show that, now let's just read out the statement, mu greater than 0 would be average loss of sweetness is greater than 0. So failed to show that the average loss of sweetness is greater than 0, then we get to say, when in fact, this was really the truth about the population. It really was greater than 0, but we just didn't detect it. So just say, when in fact, there was a loss of sweetness. In the cola. Phew, so we got it, folks. That's type 1, type 2 error in this situation. Any questions or comments on getting through that? Okay, there are multiple ways to write this out, I should mention. The way I write these out, again, is focusing on a conclusion you would actually make in a study. But if you write out something that's slightly different than this, but it really fits in what a type 1 error would look like and a type 2 error would look like, you would still get a good full credit on that kind of conclusion. But I think it makes the most sense when you write it out like this, what you would actually conclude in a real problem. Well, any questions or comments, folks, so far? Okay, I want to add maybe a little bit more to this. We have a significance level alpha here. So one question you might ask is, when would a type 1 error occur? We know it occurs when this is actually true, but we rejected it. But that would mean the p-value of the study was less than alpha at 0.05. So that means we had a significantly statistical result from the data itself, but it was an error. When would a type 2 error occur? Well, you failed to reject the null hypothesis, Yes, you failed to reject the null hypothesis to conclude this is true. That would mean a type 2 error occurs when their p-value is greater than or equal to alpha in that kind of situation. So we had a large p-value, but we were really hoping for a small one because this was the truth of the population. Our data just didn't show it. Maybe the 15 tasters were just having an off day, or maybe they tasted another cola already. Something just went awry with the study. Well, that's part A. Really kind of a long question, but it's a dang good review question. So let's take a look at the next one, part B. This one I had mentioned before. It's actually a hard question on a real exam setting. I think the reason for that is it just feels too simple to answer this one. So people usually second guess their work. But any volunteers for what the probability should be for type 1 error? Exactly. Whatever you set your alpha value to, and at the very start of the study, this would have been done before data was even collected. That is the right probability for a type 2 error. So all you have to say is alpha at 0.05, and that one's done. So that's kind of like a freebie on this problem. Almost not fair. This one's 6 points, and that one was a measly 4 points, but it's tricky, so I felt like it deserved more. So coming up next, it asks a bunch of stuff. So let's take all that, throw it in. The quality control engineer believes an effect size smaller than 0.8 will not be noticed by consumers. Now, let's pause right here. So an effect size smaller than 0.8, that means we're thinking about mu being in this range. That means, well, if it's in this range, the cola has lost sweetness. But the experts are believing that that level of sweetness loss would not be noticed by the general public. It's just too small to have any practical effect. So if that's the case, they want to design a test that is going to almost assuredly reject the null hypothesis when it's false, conclude that's true, when the specific alternative hypothesis, this one right here, is actually true. Mu equals 0.8. So we want a test that's almost always going to reject if that alternative is actually the fact. The reason it's set to 0.8 is values smaller than 0.8 just have no practical consequence, according to the experts at least. So we have a specific alternative we're working on, a sample size set to 15, and it asks us, what is the power of the test in this situation? Well, best way to run through this is we need to see what our hypotheses look like. Here they are, the original ones. After we have those original hypotheses, we have a specific alternative. Of HA mu equals 0.8. So it's greater than 0 because it's a right tail test. And once we write this down, we're just going to use essential limit theorem a couple times. And if you're comfortable, you could just drop in, put off to all the syntax and crank it out right here and now. That's what makes part C kind of a tough question. If we write down the syntax right away, that doesn't necessarily make it clear at all how or why things are working. We just have to trust the process. But if you can put in a drawing, this actually helps quite a lot. So this is a really good spot right here for reviewing for the upcoming exam too. I'm going to first draw something for the specific alternative. We'll have a normal distribution that goes about like this, centered at 0.8. And this is for X bar distributed normally. We put in the mean, 0.8. We put in the standard deviation. That means we have to look that up. I don't recall it just yet. Exactly 1. So standard deviation of 1 goes in right here through the essential limit theorem. Then we divide by the sample size square rooted, so root 15. So that's this distribution right here. Next, we do a distribution when this is true. And this is the one time where we get to say, this is why our author likes to always put equality in the null hypothesis. It's a stylistic choice, but when you get p-values or you're calculating power, it's relative to a strict equality right there. So right there, we'll use X bar distributed normally, throw in the true mean, assuming the null hypothesis is true, which is 0. Standard deviation is the same, 1 over the root 15. And the sketch to this curve would look about like this. Let me give it a little bit more overlap. It looks a little bit more clear if you overlap them a little bit more. So about like that. So that's our null hypothesis distribution, this one right here. Next thing we want is the significance level alpha, and we can start describing our syntax. Any questions to this stage, though? Writing down the essential limit theorems and the 2 sketches. Okay, one thing I forgot to add is it's always a good idea to kind of center this thing. This one's centered at 0, so that helps us out a little bit better with our scale. Next thing we can do is we'll focus on alpha. We need alpha right away. And because it's a right tail test, the area of 5% goes over here to the right tail this time. Oh, excuse me, but it goes into the one relative to the null hypothesis. So it'll be about right here. We call this value z. And the shaded area going this way, under the curve for the null hypothesis, that's going to be alpha. Probability of a type 1 error is now right there. Well, at this stage, let's calculate z. Z is going to be p norm. We give it the value of alpha, 0.05, because that's the actual value that's going right inside here for the area. We give it next the standard deviation. It's 1 over square root of 15. And because we're calculating area on the right end, we'll use lower dot tail as false on this one. So we got it, folks. That's our z. Once we get z, we're about ready to calculate power, but let's sketch it first. Power is going to be over here. The power of the test is the probability that you did not make a type 1 error, and as an area, it looks like this. So that's where power lives. That means it's not so bad to calculate. Power is going to be P norm. We give it the value of Z. Reason for that is power starts right at this barrier where we plugged Z in the sketch. But now we have to be a little bit more careful as well. If it's this area, that means it's talking about this distribution. So we need to tell it, and hang on, noticing a problem right here. I put in a value for alpha, but it looks like I missed the mean, and then I just went right up to the standard deviation. I was about to do that right here, so we need to correct a couple things. And Z would have been, yes, absolutely, that would have been a Q norm function, because we're looking for the value on the x-axis. So a bunch of weird mistakes on there. Thanks for the help with that one, Jackson. Let me put it here. Z should be P norm. There's our one letter fix. Q norm makes a world of difference. And big concern right here. Let me see if I can efficiently just move this over. What I should have done right after putting in the 0.05 for the area is I should have went here, just followed my nose, put in a 0, and then the 1. Over square root of 15 here. Then finally, lower dot tail equals false. So sorry for the weird syntax surgery. The changes are right here for Q, and right here, we had to say a mean of 0. RStudio was probably going to think of this as the mean, or probably would have had an error since we didn't give it enough values. Now with that correction, we're back on track. Z down here is fixed. So we go over here, we're calculating power. We need to give it the value of 0.8. Avoid making that same mistake again. So 0.8 first. Then next, 1 over root 15. Finally, lower dot tail, set false. So that's going to give us the power of the test. Any questions, folks, with that so far? Okay, let's run this just to make sure this thing works. That's always a good challenge here. We're going to run through power. Good syntax would be start with maybe alpha. Alpha has a lot to do with what's going to happen with the power. In our problem, it's at 0.05. We need a sample size. This one was set to be 15. And let's see, what else would we need? You know, I think that pretty much does it for power. We'll start with Z gets Q norm, alpha, 0. You know, if we want an even better syntax, let's put a little bit more up here. That way we can adjust this for any problem that ever could come up. Let's put in mu. I'm going to set that one to 0 and sigma set to 1 to match our problem. Aspen asks, can you explain again when to use Q norm versus P norm? Yes, absolutely. It's a wonderful question. I mean, that's what my mistakes right here is I started with P norm. But to tell the difference between the two of them, we would use Q norm. Let me write this way. Q norm is used when the probability is known. So that was my mistake right here with Z. I can't use P norm. I know a probability of 0.05, which was that area right there for the probability. So if you know probability, but you're looking for the value on the x-axis, Z in this case, that's the Q norm setup. And to me, that's a good way to think about it. If you have a known probability, use Q norm. A P norm is used to find a probability. In this computation here, power itself is a probability. We're looking for that area. So since the area this time is the unknown, we had to use P norm in that case. Does that make sense to folks with P norm versus Q norm? Okay, that's definitely always a good review question. And I mean, it comes back in chapter 17. Over here, we would use QT for the t distribution. And down here, we would use PT for probability with t distribution. So Q and P are going to come up in this kind of way over and over again for different probability models. So now let's see how far we've gotten along this one. We've stored a value for mu. Let's be more descriptive. Let's call that mu naught to refer to it being the value that came from the null hypothesis. Then they have to give you a value for sigma, but there's no way you can calculate probability of a type 2 error or power unless there's another specific alternative. This is what's giving us probabilities right here. Let's call this one mu A to say from the alternative hypothesis. This one's set to 0.8. And now with all that stuff is stored above, everything below is just going to give you power right away. So plug in alpha. The mean mu naught from the null hypothesis. We take sigma, divide by the square root of the sample size, so over square root of n. And because it's a right tail test, because of that right there, put in lower dot tail equals false. So that takes care of the first portion. That portion right there. Then next, we go power gets p norm. Now for p norm, we're really just doing a function composition. And you could write this as one line, but that starts to get convoluted. Put in z. Next value is 0.8. That means it's mu A from the alternative hypothesis. Sigma over square root of n doesn't change. Lower dot tail doesn't change either. That one is set to false. And this syntax is going to work for pretty much any kind of situation, but you have to change this argument to determine if you have a right tail test or a left tail test. So let's see if this works. Definitely didn't work. You usually don't expect it in the first try, but there's my problem right there. I was trying to do something more like this. Should have known that. This is the actual symbol to put in blank space. And second try, looks like it worked. And power comes out to about 92.69%. I'll put down here on the notes just the syntax we used to make this happen. That kind of formatted weird, but it works, so let's leave it as is. Well, we did it, folks. That's the power of the test. This one came out to, again, about 92.6 or 92.70% after rounding. Well, any other questions, folks, on getting through that one? Okay, let's see how far we're getting on this. So we found the power of the test when the sample size is 15 and when we're only concerned with differences as large as, as small as 0.8. Now they're asking, what's the probability of a type 2 error when that specific alternative, 0.8, is actually true? This one's not too bad, but what I probably should output here is our prior result. We found that power came out at 0.9270 after rounding. Let me know if I misrounded that or misremembered it. So now to get the probability of a type 2 error, we just have to do one extra thing. It's beta, but anyone recall how to calculate beta in this situation? Good call, folks. Jackson and Zachary. It's going to be essentially the complement rule from probability. They're complementary to each other in this sense. Power is right here. It's under this curve. And in this location is beta. That's the probability of the type 2 error. The area under this curve must be exactly 1. So upon using the complement rule, we'll find beta in this way. Beta equals 1 minus power. So probability of a type 1 error is pretty fast to calculate. Beta, probability of a type 2 error, is fast as long as you already know what the power of the test was prior. And it'll turn into 1 minus 0.9270. Let's treat ourselves to a calculator. That will be 1 minus 0.9270 for a 0.073. So pretty small chance of it making a type 2 error. And that's good because it looks like type 2 error is what it would cost the company the most. That's when they released cola, but didn't detect it actually lost sweetness in storage after they released it to the market. So, well, I mean, that might be a pretty high probability. We'd have to ask the corporation if they're willing to accept that. But we got it, folks. That's probability of type 2 error. Any questions at all on getting that one? Okay, looks like we're nearly through the problem. Let's see what else we've got. It asks, what is the smallest sample size required for the power of the test to be at least 99%? This is a definitely more practical kind of question. They're not necessarily even going to do this problem and select, where does it say? They're probably not really even thinking seriously about selecting the 15 trained testers unless they resolve these kinds of questions. If they need the power to be at a certain level because they're trying to control type 2 error right here, not let it be too large, they're going to be deciding what the sample size should be before they even collect data and let people test their cola. So here's how we're going to resolve this one. We want the smallest sample size because corporations like these are usually not willing to sacrifice very much money for accuracy, so they want it to be cheap as well. They want the cheapest test at a highest level of power. How can we find that? We just go right back to the same exact syntax we used and just start playing around with it. There's a lot of different things you can do. There's power curves you can construct and all sorts of stuff, but we're only looking at power from our introductory level, so we're pretty much just going to plug and chug, see what happens with this. Let's double the sample size at 30, run the whole syntax. Let me put one extra thing here just for convenience. Let's output power, and this tells us the answer is probably not 30. We might be able to save a little bit of money by dropping the sample size. We want the small sample size that exceeds 99%. Let's see what happens with 28. We can make it even cheaper, so if we can't do that, then they're going to require it, any corporation. At 25, it still works. So let's say at 24 is where we have a problem. We want to always give people a conservative estimate on the sample size. And being conservative means we're trying to give a large enough sample so this doesn't round to 99%, it actually exceeds 99%. So this is when we would bump up the sample size. And looks like 25 is the magic number on this problem. Right at a sample size of 25, power exceeds 99%, and that's the smallest sample that would ever make it happen. So it looks like they need 25 testers if they want a higher level of power. And how should we answer this one? We can say at n equals 25, the power is as required. It's kind of a strange problem because there's not a ton of work to show. I mean, you can just output the whole syntax, but I would assume you're using some kind of syntax like this either way to answer the question. So this is more of a paper trail for the purpose of the exam, I'd say. But we did it, folks. That's running through power, type 1, type 2 errors, and all that kind of fun stuff. And probably the more technical part of the course is all of this stuff right here. So that was a good question to take a look at. Any other questions or comments, folks, on this one here? Okay, well, let's turn it over back to the class. Anyone have another problem you'd all would like to take a look at? Oh, we have a chat right away. Awesome. Hannah says, is using power the only way we were able to calculate beta? You know, you could have calculated beta directly, actually. So back up here. If the question wasn't about calculating power, we could have done this. We could have said beta is going to be P norm Z. So we'd have to use the Z right here. We're trying to target that area to the left of that. So we come back in, grab this value, 0.8, 1 over the root 15. And confusingly, we wouldn't use lower dot tail as false anymore if we're going for beta directly. The reason being is we're taking the area to the left of Z, the direction that RStudio usually goes. So that's what we would do if we wanted to go for beta, probability of type 2 error directly. And you also ask, what power is really telling us? That is a really good question. In fact, that could be a real exam 2 question as well. Give a practical interpretation of what power really is. So let's maybe go for that portion right there. We found the power is at 99% when the sample size is 25. So let's give a practical interpretation of that statement right away. Let's come back up here. To give a good practical interpretation, we have to remind ourselves the original hypotheses and what was the value of the parameter mu. So here's some other supporting information. And still, with all this I'm putting down here, this is not enough to give a practical interpretation for power. We need one additional thing. The only way we calculate power or beta was through this right here. We needed a specific alternative hypothesis. Came from the effect size when they said an effect size smaller than 0.8 will not be noticed by consumers. So we'll grab that as well. And here's how it all comes together. You'll see where to park all this stuff. So let's interpret power being 99%. Let's see, we could say something along these lines. There is a 99% chance. Now, this is not an error. This is what we want. So I want to say of correctly concluding. Let's emphasize we made the right decision here. Correctly concluding that this is true. That alternative hypothesis was the right decision. So that the average loss of sweetness is greater than 0. Now, there's more to this. This is a kind of conditional statement. I usually say when in fact, let's say that next. When in fact, and this is the statement we're looking for, the true loss of sweetness on average. I'm saying on average, or you could say the mean, because we're looking at mu right here, is 0.8. So if the true average loss of sweetness is as big as the smallest size that they think matters, the effect size, if that is the actual truth of the population, we have a 99% chance of correctly rejecting the null to conclude average loss of sweetness is in fact positive. So that's essentially what power is trying to say. The probability of making a correct decision when you've considered the smallest effect size of practical importance in the problem. That's a lot of statements so far. Does that make sense to folks at the moment? Okay. And the next portion you asked about was for part A of exercise 4, power 0.57 says there's a 57% chance that the mean oxygen content of the stream is less than 5 milligrams per liter, but we would have to say one additional thing. Let me see if I can dig up that exercise. So that was exercise 4 of the same section. And we're looking at, for part A, power is 0.57. So you're almost on the right track with that conclusion. But the only thing that's missing is this portion right here. When it says, let me try to get these windows a little bit more aligned. One moment. So right here when it says mu is 4.75 deciliters, or just right here rather. Oh, and just an extraneous comment. This should have said deciliters as well. I have a typo in that unit, so sorry for any distraction on the null alternative hypothesis. So the power of this test should be, we have a 57% chance of correctly concluding that the mean is less than 5 milligrams per deciliter, when in fact, the true mean is actually 4.75 milligrams per deciliter. So that's how power would all come together. It has to at some point talk about that one specific alternative hypothesis. But again, that's what makes power type 1 error, type 2 error, all pretty technical statements because there's lots of things floating around. Does that help out, Hannah, in thinking about how to interpret power? Yeah, you betcha. And again, just for another reminder, anytime you go to write out a statement, say on your take-home exam 2, if it's going to be something like a type 1 error, there's always this extra statement when in fact something is true. Or for a type 2 error, something else is true. And if it's about power, same kind of pattern, we have to mention something else that's specifically true. And it's always a kind of equality. Either mu is 0, mu is 0.8, or elsewhere or otherwise. So the question was, will we need to use R for the take-home exam? You know, I'm going to keep the exam in the same kind of format since I didn't feel like changing the exam a whole bunch just because we had a snow day was totally appropriate. It wasn't really our fault that that happened, and the university was operations were canceled. So I do have, in fact, the exam already written up. I'm just going to release the exam as if it was the real exam. Other questions or comments so far, folks? Or other additional questions folks would like to take a look at? Okay, if there's not a ton of questions, then I totally understand. I think we hit the nastiest concepts the hardest. The ones about interpreting confidence intervals are pretty tough in my opinion. And anything to do with planning a study is a pretty technical kind of thing, whether it's a type 1 error, type 2 error, and so on. So I think this might be a pretty decent stopping point for us folks. I was planning on after the review going into chapter 17, but I think chapter 17 in less than 15 minutes is kind of a rough experience. We'd only go so far and have to look at it again. So this will be our official stopping point, but if you have additional questions, I'll just be hanging around here until 6:45 anyways, before my next class gets going. So if you have more questions, I'll be happy to help out. Otherwise, have a great weekend, folks. And again, on Monday, probably around noon, and I'll send an email to everyone in the class. I'm going to release exam 2 as a take-home copy. It'll be due on Wednesday, 5:30 before class. Have a great one, folks. Thanks.
Can I ask you one more question?
Yeah, absolutely.
For part B of exercise 4,
This one here?
does that have to do with increasing the effect size?
Oh, let me take a look. To get higher power against the same alternative and with the same significance level alpha, what must we do? Yeah, this one's talking about you can make a couple changes. You might potentially change the effect size, but I think another one could be changing the sample size would be another great way to go on this one.
Okay.
So yeah, I think probably sample size first would be my first thought on this, but effect size could definitely be something you could change. When it says,
Oh, sorry.
oh, no worries, go ahead.
I just think I don't understand fully what effect size is telling us.
I would say what effect size means is it's the smallest quantity that actually matters. Let's see what's going on in this one. They're talking about mean oxygen content. So if you have a null hypothesis that mu is 5, maybe you found out that the value for mu equals 5, or let me go the other direction because it's a left tail test. Maybe we found out the value of mu is 4.9998 or something like that. And you know, with a large enough sample size, you would actually reject this statement and conclude that, well, this is true. The true mean is actually less. But then we have to ask ourselves, that is so close to 5 that the difference from this and this is of no practical importance. They're just close enough to be equal. So now in this problem, when we have a value of 4.75, what the effects are trying to say is the effect size is at 0.25, and anything smaller than that, we think of as being effectively 0. It's of no importance whatsoever. It's not really going to affect anybody or anything. Does that make sense with the thoughts on effect size?
Yes. Can I ask you another thing again? Sorry.
Absolutely.
Can you pull up the graph you have with the colors and it has the Z score and alpha and beta?
Yeah, absolutely. So this one right here?
Yes. So if this was not a right tail test and it was left tail, would power be on the left side this time instead of the right side? Is that how that works?
That's the one that we did in the class lecture. In the lecture, we had a left tail test, and this whole
Yes.
thing just kind of flipped around. That's right.
Okay. And okay, I'm sorry. I just want to make sure I'm actually knowing what's happening. What is the Z telling us? It's just where it's not where the graph is even connecting. So what is it saying?
This Z right here.
Yeah.
So if you go and run through the hypothesis test and calculate, say, a Z test statistic, unfortunate abuse of notation here. Let's say this one is like a Z star, just to differentiate the two. Your Z test statistic is going to be X bar minus mu naught divided by sigma over the root of n. And if it happens to land right somewhere in here, somewhere to the right where the alpha was put in relative to that purple bar, then you would in fact reject the null hypothesis and conclude that this alternative is actually true. So sometimes this is called a rejection region. If your test statistic lands there, you have rejected the null hypothesis. But if it lands right here, you have failed to reject the null hypothesis. That's why beta is in that location. Beta is when you fail to reject something when you should have.
Oh, so it's literally just the number at which things change from accepting to rejecting.
Exactly. I think that's the best way to
Oh.
say that. Yeah,
Okay, that makes more sense. Thank you so much. I really appreciate you answering all that.
no problem at all. Thanks for those questions.
Thank you. Have a good night.
You too. And sorry, Aspen, you asked, could you run through stating the hypothesis for a couple word problems? Yeah, I'd be happy to do so. Do you have word problems, or would you like me to come up with a couple?
I didn't have any specific problems in mind, but after doing the homework last week, I think it was, homework 5, that was what I was having a little bit of an issue with, was stating the hypotheses.
Gotcha. Yeah, should be able to come up with a couple of those. Let me see what I have here for the notes. Let's see here. So I want to try maybe version 2 on the sample exam problems, just so that they're fresh problems. And let's see where we have a hypothesis test on this. This one might qualify. So it says here, and you know what, this might be a good one to just throw onto the document here. Maybe someone else might take a look at this and benefit from the question. So let's throw it down here as well. And they say the National Center of Health Statistics reports that the systolic blood pressure for males 35 to 44 years of age has mean 118, standard deviation 15. The medical director of a large company looks at the medical records for 100 employees in this age group. So now we have a sample size at 100. It finds that the mean systolic blood pressure in this sample is X bar at 116. The medical director is interested in determining if the mean blood pressure of the executives differ from the national mean of 118, the one stated above here. So there's that. Now, definitely a parameter, and we'll have a 5% level of significance. That's a lot of statements all together, but I think what's tricky about stating hypotheses is that there's very often in a hypothesis test more than one population. So there is an overall population in this problem. We were talking about all males 35 to 44, and it has this parameter value. For systolic blood pressure, it's 118. But this is not the actual mean we're looking at. We should call that one mu naught. That's just the statement of no change. When we look at the medical director of a large company, looks at medical records of 100 employees, that's the second population. We're thinking about all employees from this specific company. So we can write mu is going to be equal to mean systolic blood pressure, or these get kind of wordy, but it's for males specifically 35 to 44. But we're not talking about all males. We're looking at a more refined population of, it just says large company. So obviously a made up problem, but let's just say here in this company. So there's a lot of difficulties with stating hypotheses. There's two populations and we have to separate them out. So we're talking about a national value here, but this mean is talking about just the company. And I'd say this right here is the second difficulty of stating hypotheses. We have to write down this parameter, and that's one of the tougher problems in the whole course. I mean, that's one we started with the whole semester on, and we've always said, this is not easy. It takes a practice to get that down. Now, the third difficulty is sometimes there's words here that indicate a specific test. Let's write what we know so far. A null hypothesis would be written this way. Mu equals, and we take the value we're comparing it against, the national value of 118. The alternative hypothesis also takes mu and compares it against the national value, 118. But now we have to determine if it's a left tail test, we'll use a less than sign in the middle, or if it's a right tail test, or if it's a two tail test. And something in here has to direct us to one or the other. And sometimes something in here tells us it's definitely a two tail test. But does that make sense to so far in the process?
Yeah, so where it has that word differ in there, is that suggesting that it's not equal to?
Exactly. They're not looking for one direction or the other. Differ, just like you said, means it should be this, the two-tailed test. Good call.
Okay. So it's just
And
looking for those sort of keywords like less than,
yeah,
not equal to. Okay. That makes more sense because that's what I think I was struggling with most, was just determining which, like the greater than, the less than, or the not equal to symbol to use.
gotcha. I'd say you're in pretty good shape with this kind of stuff then. If you didn't feel too bad getting the parameter down and this stuff, it was more about that, then I'd say you're in really good shape for putting down hypotheses.
Awesome. Thank you so much.
You bet. Have a good one.
You too. Good night.